Hello and welcome to this workshop about post-quantum cryptography, where we will talk about PKI, code signing, and how to generate things like hybrid or alternative signature certificates. My name is Thomas Gustafsson. I'm the Chief PKI Officer at Keyfactor.
And I'm David Hook, VP of Software Engineering Crypto Workshop, also at Keyfactor.
Okay, the story we're going to talk about in this workshop is that the threat of quantum computing, which is a little bit hyped in the last couple of years. So the thing is that quantum computers are coming, or well, no one knows exactly when they are coming, but there's a potentially or a fairly large chance that they will come eventually in the not too distant future. And that means that the classic or encryption algorithms that we are used to, or the whole society depends on today, will be trivially broken when what's called a cryptographically relevant quantum computer will be available. So what this means practically for us working in this industry is that we will need new algorithms that are quantum resistant or quantum safe, or many terms for the same thing out there. And this has been going on for a long while and will actually be standardized by 2024. So time is coming up and it's time to prepare to make the switch and the transition to post-quantum cryptographic algorithms. As I mentioned, this has been going on for quite some time and we're nearing the finish line. So although NIST is not going to publish the new standards for post-quantum cryptographic algorithms until sometime 2024, early 2024 actually, CISA and NIST and all other basically government organizations strongly recommends organizations to start preparing for the transition now.
So fortunately, NIST haven't just dumped us in it and just said we all need to get going. They have actually provided some guidelines to explain to people what to do. So what I'm going to talk about briefly now is what organizations should do to prepare. So the first one, of course, is identifying where and how public key algorithms have been used. So this is just the important part of actually knowing what it is that you're currently doing, so you really do understand what you need to replace. The second one, of course, is mitigating enterprise risks by providing tools, guidelines, and practices that can be used by organizations in planning replacement and update of hardware, software, and services. So again, this is like having worked out what you're doing, you then actually need to work out how you're going to deal with it. And this is going to require replacing software and hardware. Make no mistake. Finally, there's the whole idea of just developing a risk-based playbook for migration. And the idea here, of course, is the organization needs to address what risks it's facing and then work out what procedures need to be in place for people to safely migrate the software and technology they're using to a quantum safe environment. So other government recommendations that have come out, which also explain the relative urgency which everything's going on with, is this infographic that's actually from Homeland Security in the United States. And as you can see, 2024 is the year, as Thomas mentioned earlier, where the initial standards will be published. And then 2024 is also the start period of the transition to be taking place. And then hopefully everyone's going to be there by 2030. So this is quite an aggressive schedule, make no mistake. And yet it really does mean that we need to start preparing for this now. Regardless of whether or not, of course, quantum computers actually suddenly arrive, the fact is that this is actually what government and financial sector organizations are going to be expecting to see in place. We have 3 standards that NIST have currently published in draft. We're now at the beginning of a 90-day comment period. We expect to see these standards finalised probably in January next year. 2 of the standards are for signature algorithms. That's the ones formerly known as dilithium and formerly Sphinx Plus. And then Kyber is actually a key encapsulation mechanism. So you'll see that getting used in things like TLS and for transferring keys. It really takes over from where RSA was originally. There's also round 4 going on. This is boiled down to two algorithms, BIKE and HQC. There's a third algorithm left in there at the moment called Classic Michelise, but that is actually already been standardised outside of NIST. The question will really be from their point of view whether they're actually going to join in and have a standard of their own. These algorithms are different from Kyber and dilithium, which are both lattice-based. These are actually code-based. So what they're actually looking for is the ability to build a slightly broader sort of gene pool, I guess you'd call it, to make sure that, if one algorithm turns out to be not so great, they can actually move to something else. To get more signature algorithms, they had 40 submissions initially. At the time this slide was written, there were 30 that were still surviving. 7 of these algorithms are lattice-based, although NIST's expectation at this point is they probably won't standardise any more lattice algorithms unless there's a very compelling reason to do so. And I think the 30 still standing number is actually now wrong. It's probably slightly lower than that, but not by much. One of the interesting things to note, of course, is there's actually variants of an algorithm that's already been accepted, which is Sphinx Plus. But it's actually based on the ASCON family of algorithms, and ASCON, if you're not aware of it, was the algorithm that was chosen by the NIST lightweight cryptography competition earlier this year. So, specifically built for small devices and IoT. And of course, a process of actually drafting up documents for describing public and private key formats. And as we'll see later, also additional certificate extensions and support for things like that to assist with migration. One of those also being X509, which has what's called the alt extensions. These give you the capacity to include an extra signature or an extra public key in the actual certificate that you're generating. And these, of course, are managed by X9, the financial standards organisation. And message syntax, certification requests, certification management, and as I mentioned before, migration to quantum ready. These are all being done by the IETF.
And briefly mentioning Keyfactor's quantum ready solutions, the Keyfactor portfolio includes components for all the recommended steps for a migration to post-quantum cryptography. First step, of course, is inventory. So there's a Keyfactor command which handles certificate inventory, TLS scanning, you name it, to inventory the cryptography and certificates you have in your organization. And then we have technical components to actually do the migration. Bouncy Castle cryptographic library, of course, that implements all the cryptography, the messages, certificate formats, everything that David just talked about, and EJBCA and SignServer, which does certificate issuance and digital signatures like code signing, respectively. And finally, for actually automating the migration for systems to replace certificates or renew certificates, etc., Keyfactor command have automation facilities to both distribute new roots of trust and migrate end user or device certificates. And not going into details, but there's a quite significant roadmap, of course, kind of taking a stamp from the milestones that David mentioned briefly as well, like the publication of NIST of the final or first initial standards in early 2024, and moving on to things like the CNSA 2.0, which mandates vendors selling to the federal government in the States to move to quantum safe algorithms for firmware signing, and moving on for 2026 and onwards, where different governments and organizations will be mandated to switch to algorithms. So of course there's a whole range of technical features that will fit into the time frame in order to make all products and the whole migration journey as smooth as possible for customers and users.
I'm just going to look at what we're actually doing in Bouncy Castle, which is the low-level library that's supporting a lot of this. Essentially, a lot of it's just about following the standards as they're evolving, because they are constantly changing, and this is an important point to get across at the moment. While you're preparing, you also need to be aware of the fact that the algorithms are being tweaked constantly, and it won't be until NIST finally issue the final standards that you'll actually have a stable platform on which to work. The algorithm changes at the moment are quite minor, but yet in terms of being able to generate long-term certificates and things like that, you'll actually need to wait till the final standards. So the second thing we're trying to deal with is, as we were talking before, certificate modification. We're providing mechanisms that have been mainly reviewed by the IETF or X9 to actually support things like alt certificates, Delta and Chameleon extensions, the composite certificate construction, and certificate binding, the last three all being IETF drafts in various stages at the moment. Finally, of course, with all this comes updates to how things like cryptographic message syntax, certificate management protocol, certification request formats. For example, chems can't actually be used to generate signatures under any circumstances, unlike, say, with RSA. And then, additional cipher suites and things like that for protocols like TLS.
So, and then we're going to go into demo time. So we're going to show a couple of demos and things that you can do with EJBCA, SignServer, and Bouncy Castle. Okay, and first disclaimer or warning. You can't mention this too many times. David already mentioned it once. But usage of post-quantum cryptographic algorithms at this stage is for non-production use only, because they are changing until the final standards are out. And they are not expected until early 2024. So anything you do today will be completely non-interoperable and will have to be torn down once the final standards are out. So what we will show in this demo is creating a post-quantum PKI first. And before we get started with that, there's a prerequisite which there is an online tutorial for, of course, and that is to install EJBCA, or actually start it as a container. That's the easiest piece. And then issue a client certificate to both access the EJBCA administration interface and later on to access SignServer for the second demo about code signing. So what we need is to have the EJBCA container started, as I mentioned, and we will also have SignServer installed and started with access to all administration UIs. And now, in the first demo, I will show how to create a CA hierarchy. We will start by creating a root CA, or a trust anchor, root of trust. Nice child have many names, as you know. After that, we will create a sub CA, also known as an issuing CA, which will later, in the second demo, be used to issue an end entity or code signing certificate to actually sign some code. Okay, let's start. Okay, so now I will hopefully do a successful live demo. What I have done before this demo is, as I mentioned, gone through a quick start guide to starting EJBCA, issuing a client certificate for authentication, and second, I have made a quick start for SignServer, starting SignServer with client certificate authenticated access. So I have both these running as containers, and now I will jump into the EJBCA, create a post-quantum PKI with EJBCA. So here I have my EJBCA administration interface, and I will pretty much follow the tutorial, so it will look and feel just like if you were doing it yourself. So to do that, I will first start by creating two certificate profiles, one for the root CA, as I mentioned, and one for the sub CA. So in EJBCA, I go to certificate profiles and I create this my PQC root CA profile, and I will edit it. And it's a root CA profile. I will use dilithium 3 signature algorithm for that. I can use pretty much most default values. And that's it. And second, I will create a sub-CA profile, which is pretty much the same. That for a sub-CA, so it will call my PQC sub-CA profile. I will do the same there, edit that one, be a sub-CA profile, also use dilithium 3 for this. I can play around with the maximum validity periods, of course, so I will shorten that a little bit. And that's it. Second step is to create crypto tokens to actually keep the digital signature keys for the CAs. So I will create one crypto token for the root CA and one for the sub CA. So for do that, I go into crypto tokens in EJBCA. I create a new crypto token, first for the root CA, called root CA PQC. We'll use it as a soft crypto token. I will give it a password and create it. And then I will create keys, of course. I will create one sign key, that is dilithium 3. I will create a test key. This is something that EJBCA uses in order to test online. If you're using monitoring of the system, it can use that to test that everything is working as it should without actually using the CA site signature key. And I will use also an encrypt key, which at this stage will be a normal RSA key. This will not be used, but it can be used by the CA to encrypt certain things in the database. For the time being, we'll have to live with RSA for that. Second, I will create a sub-CA crypto token called sub-CA PQC. It will be very similar or virtually identical, you could say. I've used dilithium 3 here as well. There's a sign key, there's a test key, and there's an encrypt key. So that's that. Now we have everything prepared to create certification authorities or certificate authorities. So looking at the tutorial, it suggests to use PQC root CA for the root CA. So I will go to certification authorities in EJBCA. I will add a CA called PQC root CA. And I will select my root CA PQC crypto token. And since I will want to use dilithium 3, I select dilithium 3, and well, it's clever enough to figure out that I want to use the sign key to sign certificates and CRLs, and the test key for test key, and encrypt key for anything, something else, which we does not use. I can copy paste here from the tutorial for the subject DNs or subject and issue DN, since this is a self-signed root CA. And I can give it a validity of, say, 20 years, for example. It's whatever you want. And then that's it. I can click create, and I have my root CA created. And I will do the same for a sub CA. I will call this PQC sub CA, and I click create, and I do pretty much identical, but with some minor changes, but so important. I'll use the sub CA PQC crypto token in order to use the sub CA keys. It's important that it's definitely not the same keys as for the root CA. The same signing algorithm, dilithium 3. I could have used dilithium 2 or 5, but let's go for 3. Keys are nicely selected. I will use another subject DN for the sub-CA, and this one will be not self-signed but signed by the PQC root CA. So the issue DN will come from the root CA. And I will give this a slightly shorter validity, say 10 years. And that's it. And I can click create, and I have my sub-CA and root CA. So if to finalize things, I can just look at the hierarchy and see what it looks like under basic functions here. I have my root CA and the sub-CA. And for the downloading of certificates, I can download the root CA certificates, and I can download the sub-CA certificates, so I have them stored on disk. And that's it for the tutorial for creating a post-quantum PKI. So now I will try to perform a live demo of SignServer post-quantum signing. It's always a bit scary with live demos, but I will follow the tutorial, which you can find online there as well, for SignServer post-quantum signing with the different steps. So the step S1 is to create a crypto token in SignServer. So as the prerequisite, I have a SignServer running with access to the admin UI. So for that, I will create a new worker from a template, which is a key store crypto properties template. I will click next, and then there's a couple of properties I need to change. I will use key store type internal, and for that I don't need a path. So with that, I apply, and then I can activate, which will actually create the internal crypto token. I will give it the password and activate, and that should be done. And then the second step is to create a signing key. Going to crypto token, and I generate a key. So the tutorial suggests that the key will be called CMS Signer. So I will use that. CMS Signer with the dilithium to key specification. Generate a key, and we have a key. Next step is to create a signing worker. That's the worker who will actually create the signature. For that, I will go to the Workers tab again and add a new worker from a template, which will be the CMS Signer properties template. And clicking next, I get a bunch of properties here as well. And also here, I will change two properties. One is the default key, where we will use the newly generated key. The default key, changing from the template to that, and we will use a detached signature for this signing demo. And we also have to set the signature algorithms. So we will find the property that talks about signature algorithm there, and I can copy paste from the tutorial again. Signature algorithm should be dilithium. So set it to dilithium, and then we can click apply. Good. Then we move on to the next step, which is to generate a CSR, or certificate signing request, in order to be able to sign a certificate or issue a certificate from the CA. So we will select the signing worker and generate a CSR with the name suggested in the tutorial here. So we'll select the CMS signer and click on generate CSR. We only have one key, it's dilithium, that's very good. So we'll give the CN equals CMS sign for the CSR. We'll generate the standard CSR and click generate. then a download button magically appears, and we can click that, and we get our CMS Signer P10 CSR downloaded. So all steps are quite small in itself, but there are many steps. So you have to keep your, how do you say, tongue in the correctly. So the step 2 in the tutorial is to issue the signing certificate from EJBCA. Then we remember we have our EJBCA created that we played with before in the previous demo. And we will go back to that to create a new certificate profile and identity profile and to issue the certificate. So I switch to another browser window where I have my EJBCA. And I will go to create a certificate profile for that. And again, the tutorial suggests a good name. CMS Signer. I will use that name. I will add a certificate profile. I will edit this. Oops, that was the wrong one. The CMS Signer certificate profile is what I will edit. It's an end entity certificate profile. I will only allow dilithium 2 key pairs. I will let it have a maximum validity of 2 years. It will only use digital signature. As David mentioned actually before, you cannot, or hinted at, you cannot use key encipherment for signing keys with these post-quantum keys as you could for RSA. So digital signature is the only key usage we will use, and that's good. We will save the certificate profile. And next we'll create an end entity profile. Also here, the tutorials suggest to use the name CMS Signer. We will use that. Click on End Entity Profiles in EJBCA. Add a new one called CMS Signer. Add profile. And we will edit this. So we'll make it fairly simple. We will not use an email. Common name will be a field we will use. We will of course use the CMS Signer as default certificate profile. We will issue the signing certificate from our post-quantum sub-CA. And we will use what we call a user-generated token, which means that we will send in a PQC10 CSR. That should be it. So we can click Save, and then we're ready to issue a certificate. Again, looking at the tutorial, it tells you how to do it. We will go to the RA web and make a new request. We will select certificate type CMS Signer, key pair generation provided by user, which means that we will upload the CSR we created called CMS Signer.p10. Select that. You can see that it has correctly a dilithium 2 key algorithm. CMS Signer is a good common name. We will use the same as the username in EJBCA. And we will download the PEM file with a full certificate chain, which means that the downloaded file will contain the CMS Signer certificate, the post-quantum sub-CA certificate, and the post-quantum root CA certificate. So it's downloaded, or the certificate is issued, the chain is assembled, and it's downloaded. It's fast as click of a button. The third step here is to download signing certificates as well to be able to store them actually to use as parameters to the verification procedure, which is the last step. So since we are in EJBCA, we will do it once we're here, so we don't have to go back and forth. So I will download the post-quantum root CA certificate and the post-quantum sub-CA certificate. So, done that. Back to the tutorial and SignServer. Now we are ready to activate the signing worker in SignServer so we can actually do some signing. So to do that, we will go to SignServer, to workers, we have our CMS Signer worker, which we can select and click Install Certificates. Here it pre-selects the default key, CMS Signer. It has a browse button that will browse to our issued certificate chain, which here is called cmssigner.pem. It's a default name given when downloaded from EJBCA. So select that and click Install. We have to click Add first, of course. Then we can see all the certificates that are in the file, and we can click Install. Then it's done, and the CMS Signer is active. It changed from offline to active. Last or second to last, but absolutely not least, is to actually sign a file. So this everything we have done up to now in 2 demos is in order to do this single step. A lot of work for small things, but don't despair. Once you've done it, it's easy, or you can sign many times. So we will use the SignServer client web to sign a file. So we will go to the client web. We will use the CMS Signer worker. So I will copy and paste it so I don't accidentally type the wrong name. CMS Signer worker, and for input I will put any file that I want to sign actually, but I will sign my cmssigner.pem certificate chain. It's good a file as any to sign. So I will select that in the browse and I will click Submit, and I will actually get a detached PQC 7 or CMS signature downloaded. So now we have done everything we set out to do. We have created a post-quantum PKI, we have created a post-quantum signer, we have signed a file with the dilithium 2 post-quantum algorithm. So the last step would be to verify the signature. For that, there is a command line verification tool, which we will use. And in order to do this, we will need to move a couple of files into a trust directory, which are the trusted CA certificates in order to verify. So I have prepared a directory for to upload certificates called trust. So I will copy the PQC root CA certificate into the trust directory. I will copy the PQC sub CA certificate to the trust directory. Done. And then I can run a verification command. So I have a post-quantum verifier Java program, which takes as input the signature we created and the file that we sign. So it can verify, it takes the file and wants to see that it has not been altered. It does that by using the signature or verifying it using the signature. And it verifies trust of the signing certificate up to the root CA certificate. So I run this command and lo and behold, it works. So it says it adds the root CA as trust anchor. It also adds the sub CA as a trust anchor or a chain. It verifies the signer we call CMS Signer. The algorithm is an object identifier, which is the temporary object identifier for round 3 dilithium 2 version. And it says that the signature is trusted. So that's pretty much it. All the steps in the tutorial from signing to verification is done. So good luck.
All right, so now for something completely different, I'm going to look at actually doing some scripting to create one of the hybrid certificate modes that I was talking about earlier. The one I'll be demonstrating is, or showing rather in code, is the one that's been specified by X9, which is the alternate certificate type. It allows you to include a second signature and a second public key in your certificate. So just a bit of quick background before I start on how this actually works. We've basically got a command line language written in Kotlin, and it allows you to do things like generate root sub-entity certificates, all in a simple way. It's got support for the FIPS candidate algorithms that are supported in Bouncy Castle, so the Kotlin API is actually built on Bouncy Castle. It's really designed for doing small things though, so you can do tests and things like that. And of course it has hybrid certificate support. So if you look at the second last line, you'll actually see there is the URL where you can actually find all this. And the only thing I'd just like to get across is that because, as we both mentioned earlier, things are changing, you want to be using the beta if you're going to try and do this at home. And you can get the beta at bouncycastle.org/betas. So, initial setup for a certificate. With Kotlin, we basically just specify the key pairs. In this case, they're both signing key pairs, and we've got an RSA one where we're using a 2048-bit key size, and a dilithium one where we're actually using dilithium 2 as the parameter set. I've got a couple of other variables here just to show how this is set up, but I've set an expiry date, and I've also given a default subject name that I'll use later in the script. So the next block of code I'm going to look at is actually where we create the first part of the alt extension. In this case, we're only providing the public key. I'll actually show how the alternate signature is added later. You can see though that this is a standard certificate extensions block, again specified in the Kotlin DSL. The first two extensions, of course, don't need any introduction because they're all standard. But you'll notice that the third one is a thing called a subject alt public key info extension. And it's this extension that actually turns the certificate into a hybrid certificate. So what we're doing here is we're specifying a second public key that will be included in the certificate. And in this case, of course, it's dilithium. So finally, we get to see where the extensions are added. That's actually what would be next to the extensions equals assignment in the middle. And if we look just above that, we can actually see that we've got the RSA verification key being added. So that's the standard key that you normally see in a certificate without the alternate one. And then underneath the extensions block, we actually see the first signature, which of course is actually based on the RSA key. In this case, we're just using PKCS 1.5 and we're using SHA-256 as a message digest. The next one, of course, is the actual alternate signature. Now, this also winds up in the extension block of the certificate, although it's actually hidden in the script. And in this case, it's just dilithium, and we're using the signing key corresponding to the dilithium public key that we added in the extensions block that I showed previously. Just a couple of other things you can do in Kotlin, apart from specifying certificates. Obviously, you can write them out. You can write out the keys. So we've got some standard extensions to allow for the creation of PEM objects, and also for doing things like certificate management, messages, and PKCS 7, which is the second one here.
And last but not least, we would like to make an introduction of the PQC lab. It has actually been up for a little while, so it's a web page on our homepage with resources where you can stay up to date with the latest innovations from Keyfactor related to post-quantum cryptography. And it, among other things like pointing to EJBCA SignServer and Bouncy Castle, it also gives you pointers to where you can create your own lab environment with Azure and AWS trials, and of course all our open source software that we've been talking about today. And educational information or resources that you can share with your leadership in your organization to start and prepare your organization for the post-quantum migration. Thank you.
And thank you.